Assalamualaikum warahmatullahi wabarakatuh. Now, our chapter 10 consists of around 8 subtopics. So, 10 up until 10.6 coming from consisting the idea of object rotating. And then we are going to look at what if the object is in equilibrium. And for that case, we have to jump into chapter 8. Alright, now let's have a look at the book. Now, in chapter 10, overall we can say that you will learn that object when it is in a rotation motion will also experience displacement. So this displacement will have a new name where we call it as angular displacement, angular velocity, angular acceleration. So all what you have learned in the linear version, especially the kinematic expression, we are going to use that idea but somehow mimic or mirror it to what we learn in this topic as object move in a circle. That's number one. Number two, we move a little bit upward where we call it torque. However, it's very much related to what you have learned for Newton. If let's say that when you learn about Newton, object accelerate because it experience force. In this case, object experience angular acceleration because there is torque. Right, let's start with understanding quantities belonging to angular motion. So we find whatever we have seen in chapter kinematic or the very earlier topic, for instance, displacement, position, speed, velocity, acceleration is still relevant. And therefore, in this case, you find that when we treat ataupun kita discuss in the form of angular, we just add on the terms angular position, angular displacement, angular velocity, and angular acceleration. So in short, everything is very much based on the terms or on the case, the measurement of the angle, where we will start measuring the angle in the form of radian. Now, this is an example shown here where you have a blue ray disc that rotates. Okay, so as it rotates, now there is one position here that initially, as in this figure, originally at time 0 is here, but as it rotates, you find that the position appear to be moving and rotating at an angle theta here. So the displacement that he has traveled would be measured in the form of angle, which in this case is the angle itself. Now, the most common question asked by the student, why did we have to treat angle or motion in a circular by using the angle? Because for instance, if you keep seeing things in a form of linear, right, the point P, the moment it complete one circle, it will reach the same position here. So end up in the version of the linear displacement, you arrive with delta displacement equivalent to 0. So that's the reason why everything when object move in a circle, we measure it in the form of angular perspective. Alright, to take notes on the directions, very simple. The moment that the object is moving counterclockwise, we will consider it as a positive value. Why? Because the angle is measured right from positive x-axis, above positive x-axis. So counterclockwise is positive, direction of rotation clockwise is negative. Related to what you have learned in high school, you find that the angle is actually the ratio of the arc length divided by the radius. So therefore, as you rearrange the expression, it becomes S equivalent to R theta. Now, I'm listing down all the related expression here, whereby SVA is actually the linear quantities. So this is technique, or this is equation how you can convert all the linear product or linear quantities to angular quantities. So we have here S equivalent to R theta, V R omega, and A r alpha. Now what is theta? Theta is the angular displacement, omega is angular velocity, and alpha angular acceleration. We learned in high school as well that angle can be measured, or we can portray angle in two versions, radian and also in degree. So something to recall again, that a product of one single pi is equivalent to 160 degrees. So this is how you can convert it into radian. Now, in this topic as well, you will find the situation you have seen earlier in the linear quantity where kinematic occurs would be applied, and in that sense, all the kinematic equation would be replaced by another quantities where yet portraying the same expression. But nevertheless, whatever you have learned earlier, for instance, displacement, then therefore we find that adding on the angular displacement to measure displacement but in the version of the angle, which in this case is radian. What about average angular speed? The same thing that you have seen earlier in the version of average speed, whereby displacement divided what? By time. So in this case, it would be the angular displacement divided by time. It goes the same as well with instantaneous angular speed. Average angular acceleration, you can see now the introduction of the kinematic expression. And finally, the instantaneous angular acceleration. So whatever you have learned previously, they still valid, except that whatever you seen in the for instance, the V turns into omega, the displacement becomes theta, and finally the acceleration becomes alpha. Before we proceed to the next subtopic, we are going to see another way, another perspective, another technique on determining whether the direction of the omega is positive or negative, where we are going to use what we call as right hand rule as in the figure. Now this technique required us to understand that our thumb would be the direction. If our thumb shows out of the page, that is considered as positive. If it's into the page, that's considered as negative. Alright, while the rest of your fingers, okay, should be in the same direction as where the rotation occur. Now, go back to this figure 10.2. In this case, the arrow, the curve shows or indicating that the rotation is in this direction. So, curl your finger in this direction, or the other four finger, or the four other fingers in these directions. While you will find that your thumb would be pointed out of the book page. In this case, you will find that the direction of the angular speed or velocity is a positive value. And again, I must mention that you can see it in this other version as well. You find that the measurement of the angle is being measured from positive x-axis, from above positive x-axis, and that makes the angle being measured as a positive value. What about if it's a negative value? Then the thumb should be pointing into the page. And this is what this figure 10.3 try to portray. If it's clockwise, then it becomes negative value in terms of the direction. Let's go another step ahead. So 10.2, where the scenario is we have constant angular acceleration. So this is very similar to kinematic expression that you have seen earlier. For instance, the kinematic expression of V final equivalent to U plus AT, we find that we can jot down as omega final. Recall again that V and omega are correlated to one another. V are the linear quantity. So these are linear quantities. These are linear quantities and these are angular quantities. You find that the expression are similar. So if you can remember this, then you should be able to memorize this as well. Okay, nevertheless, before we proceed with example, recall again that x displacement or distance is now being measured in the form of radian or angle, and acceleration is alpha, and their relationship is, recall that S is R theta and this is X actually, and V is R omega, and finally A is R alpha. And bear in mind, this is what you have seen earlier in previous subtopic of rotation, V tangent and A tangent. Now let us look at this additional example. In this additional example, we are going to use kinematic expression. However, we will find that alpha would be 0 and therefore omega is a constant product. Just to jot down your memory once again, that delta x is ut plus half at squared, and we're going to put this as 0 and writing this expression again in the form of angular quantities. So delta theta omega t got initial. Now the aim of the question, we have two aims. Number one, we are going to do conversion from units revolution to radian, and we have another conversion from unit radian to meter. Given in this question, the rotor of a helicopter, maknanya bilah dia, turns, berpusing at angular speed 320 revolution per minute. Maknanya dalam 1 minit ada 320 pusingan. So, express this angular speed, this is actually omega, however in unit RPM, not radian yet. You have to express this unit RPM to angular speed in the version of radian per second. How to do it? Now, look at this value just now. What we are going to do is, one revolution is equivalent to 2 pi. 1 minute is equivalent to 60 seconds. So mathematically becomes 320 times 2 pi divided by 60 seconds and arriving with this answer. The next question B, if now radius is given, what arc length does the tip of the blade trace out in 300 seconds? Was trying to portray, if now you have the radius, they want to know in within 300 seconds, what is this? The arc. Okay. So what to do? Recall again the kinematic expression earlier, that delta x is ut plus half at squared, substituting a as 0, and therefore alpha turns to be 0 and the expression left with omega times t. And you can see here, this is the omega and this is the t. So within 300 seconds, the angle you have covered is 1.01 to the power times 10 to the power of 4 radian. So let's say that you are interested to know the value in the form of meter, the arc length. So you need to go back to the linear quantities earlier, which would be S equivalent to R theta. And the whole theta displacement within 300 seconds is 101 to the power times 10 to the power of 4 radian. So times with the given radius just now. So this is the whole circumference or the whole arc's distance that travel by the tips of the blade within 300 seconds. Now let's turn back to our textbook. Before we proceed, just recall again the process or the kinematic expression that you have seen earlier in previous topic. V final equivalent to U plus AT. So really similar to the linear kinematic expression. Okay, so make sure you trace again this expression and match with your new understanding. Okay, cuba tulis semula expression ini dalam bentuk angular with what you have understand previously in the linear relationship. Now, example 10.1, rotating wheels ni, this time around, in this example, we are going to use the kinematic expression whereby there is a value of acceleration. In this case, kita nampak bahawa a wheel is rotating with a constant angular acceleration. So, angular acceleration ada value, which in this case, the value is 3.5. Now, notice that 3.5 is your alpha. Angular speed at time 0. So this is your initial omega. And through what angular displacement it's asking for? Delta theta within time frame 2 seconds. So the expression that recall for angular value, we have two. Number 1 this, number 2 number 3. So we have 3 expression. But which one fit straight away to get to the request question? So we find time is given. So we can choose this and we can choose this one. Alright. So for this one, the book choose 10.7. 10.7. Okay. Delta x is ut plus half at squared. So this is omega initial. Okay. Therefore, you find substituting it, t is 2 squared, alpha is 3.5, and omega initial just now is 2. And arriving with answer 11 rad. Okay, notice what I did just now is, I need the kinematic expression and I need to understand what is this 2, what is 3.5. So another way of looking ataupun cara nak memahamkan dia, look at the units. Odd theta has the units of radian and theta is displacement. V, where resembling angular quantities omega, the unit will turns out to be radian per second. And therefore alpha, which is the acceleration, becomes radian over second. So look closely at the unit so that you don't get confused. But nevertheless, another technique to not get confused is straight away look at here, acceleration, speed, displacement. So start with what you have understand earlier regarding linear quantities, and then only you look at the front version, which is angular, the frontwards angular acceleration and such. For the exam purpose, the angular displacement is actually sufficient to provide the answer as 11. Cukup dah. Okay. However, if let's say that the question would like you to convert into angle, then do so. And how to do it? Notice that the technique used is 11 rad times 180 over pi. Or you can use times 300 over 2 pi. So long that you understand how to convert it. B, through how many revolution? So one revolution is equivalent to 1 turn, which equivalent to 360 degree or equivalent to 2 pi. So what you can do instead, okay, this technique, beside using this technique, you can use this technique. 11 divided 11 rad divided with 2 pi rad. You would still arrive with this one with the understanding that if 1 turn is 2 pi, then what about 11 radian? Okay. Now for question C, it's interested to find the speed, but at a specific time. So for this one, require us to go back to the linear expression V equivalent to U plus AT, and therefore V final is omega final, U is omega initial, and A is alpha. So substituting correctly will arrive you with this answer, radian per second. You have seen earlier the idea that what happened when object experience rotational acceleration. So this time around, we are going to go a bit deeper, whereby rather than just simply use S equivalent to R theta, we're going to consider as well the rest of the linear quantities. For instance, V tangent is equivalent to R omega, A tangent equivalent to R alpha. Another take home message that you have to consider as well. Remember, when object move in a circular motion, hence indeed there will be towards the center force, which is centripetal force, and in this case there will be AC towards the center. Now the AC is here, R omega, which is V squared over R, and therefore equivalent to simplified version of R squared omega 4. In the previous example, you have seen what to do, technique using kinematic, however using angular kinematic when involved angular acceleration. This time around, we're going to go a bit higher, whereby we're going to include more linear quantities. For instance, previously we have seen only S equivalent to R theta. Recall that S is the circumference or S is the arc. And here we have another two more, which is V tangent R omega and A tangent R alpha. Now, since we are touching concept of A here, recall as well, when object undergoes circular motion, indeed there will be what we call as centripetal acceleration towards the center. And in the case where there is a change of omega at the of the object, therefore indeed we will observe there is a product of R alpha or A tangent, okay, in this case, and simultaneously at the same time we have what we call as AC here, so A total. So you have seen this earlier in the previous topic. Alright, to use the idea of all the linear relationships with the angular, okay, so let's look at this example, which is compact this. We are going to use the kinematic equation and then add on with the value of linear values. So the case is we have a compact disc. It rotates starting from rest up to angular speed, omega final, and hence this is omega initial equivalent to 0. So this is the time given. Question is, what is angular acceleration? Angular acceleration here is alpha, assuming that angular acceleration is uniform. So remember the kinematic expression where V final U plus AT. Well, we are replacing V with the omega. So given here omega initial as 0 and omega final as 3.31.4. Substitute accordingly, including the time you will arrive with 35.2. So the value indicated here is a positive value because we find that from 0 and then increased in value. Now for the B question, when it start asking you through what angle, the angle represent theta. So the expression that we are looking for is x delta x ut plus half at squared. Right? And with that, you'll find that omega initial just now earlier is 0 and alpha had been calculated earlier, which is 35.2, and time is similar as given in the original question. So arriving with 14 rad. Now, since the question does not ask you in terms of the unit, so you can leave it as 14 rad, because with 14 rad, you can use for the next question. Let's proceed with the next question. If the radius is now 4.45 centimeter, find tangential speed. Now, what does tangential speed represent? Go back to the linear expression, linear quantity relationship between linear and angular, which is VR omega. So the omega had to be the omega during the time of 0.892. So it means that this is at omega final, and that's the reason why we are using 31.4 rad per second. So in short, find tangential speed at 1 second, 2 seconds, 3 seconds. Why? Because we find that V value dependent on the omega value. So you have to be very specific in terms of the time to refer of the value of angular itself. So in this case, we arrive with 1.4. Finally, what is the magnitude of tangential acceleration at that given time? So the whole process required us to understand that during the whole process, during the whole rotation, there is just one single value sahaja. So this is a constant product. So it's not like for C whereby the omega changes with time. So in this case, we find that it's just purely substituting or times with the R value here and arriving with the unit of meter per second squared. Okay, give it a try.